As is often the case with meta-scientific work, people often start with what they suspect personally might be a particularly bad example, and then we generalize across to broader literature because perhaps we're not interested in merely the CRTT, but the flexibility of measurement across tasks generally, in which case it's useful to select tasks based on how commonly they're used, for example. So the Iowa gambling task was a candidate for a similar meta-methods review, right? It's a very commonly used task, especially in neuroscientific and cognitive neuroscientific work. It takes the form of a computerized card game, and it's said to measure real-life decision-making or risk-taking behavior. And this is often done in the context of neurological impairment in the original evidence, and now in psychopathological deficits as well. This is work in conjunction with Annika Kultman that we're doing. We still haven't published yet, so take results with a slight grain of salt. Okay, to explain what the task looks like, you are presented on screen with 4 decks of cards, and you are asked on each trial to draw from a specific deck. So you have to choose which deck to choose from. And after each trial, you are given feedback on whether you won money and also separately whether you lost money. Wins and losses can differ between trials. So on some trials, you may only win the $50, and on others, you would also lose money. Some decks are also different to others. So the decks differ in the contingencies programmed into the task, and thereby we provide a way for participants to make decisions under risk. So some decks are particularly risky and some good. And which decks are better and worse can only be learned across trials through selections and switching between decks. What did we do? Following a similar procedure established in part by Malta, a systematic search was used to find the full population of studies using the IGT. And because it's simply too large to inspect all of them, the same as we would do with participants, a subsample is randomly selected. And we extracted details of the procedure and the scoring separately in order to observe heterogeneity and variation. So very briefly, where did we see flexibility in details of the procedure? At the top line, whether the goal of the procedure and the instructions of how to complete it were to vary substantially. The win-loss contingencies between decks can also vary between tasks. The number of trials involved in the task can range quite greatly, and the number of blocks. Several other variables we extracted too. The most notable point here was that the modal classification for any variable in the procedural details was that it was indeterminable from the paper itself. So if you're looking to be able to evaluate not only the results of the paper, but the method that generated that paper, the modal case is that at least one important detail is indeterminable from merely reading the paper. So one of the challenges here is not merely observed flexibility and heterogeneity in the implementation of the procedures, but the indeterminability of what actually was done to generate that data. Similarly, when it comes to scoring, multiple classes of scoring methods could be abstracted from scorings reported in the paper. The most, not the most common of which, but a still common category of which was it simply being indeterminable, where researchers simply reported that the Iowa gambling task was used and scored, but not specifically how. You can categorize these scorings into several initially intuitive categories, but running into the same problems that Malta observed via their sheer number. You can categorize them based on their earnings, the total money won, although a critique of this would be that it ignores the probabilistic nature of wins and losses, because you're now introducing luck into your scoring strategy based on which cards participants happen to get. You can also do it based on deck selections. If we call the decks A, B, C, and D, you can count the number of choices from decks A, B, C, and D, and we observed each of these in the literature, as well as other combinations like the combination of decks A plus B and A plus C and B plus D and C plus D. And more again, you can calculate the proportion of good decks, those that tended to produce wins at a higher probability, which are decks C and D, as a proportion of the bad choice decks, or indeed the difference between them. Or you can do this only in the subset of early trials, and you can vary what you define as early. Is it the first less than a fifth of the task? Is it the first 40%? You can also do this in the late proportion of the task, on the perhaps theoretical notion that performance should stabilize across the task as participants learn which deck is which. But again, you will see variation in the proportion of the deck that is defined as what constitutes late. And now that you have early and late trials, similar to how Malta observed that scores tend to be combined in novel ways, you can also have different scores between them. So you can have scores following the modal scoring of C plus D minus A plus B in the late trials, divided by those in the early trials as an index of learning. And perhaps there is theoretical, perhaps that is theoretically sensible, but it's difficult to know in the lack of standardized usage of scores like this across papers. You can also have, you can also score the data using switching behavior, of which we observed a number of what were quite heterogeneous and particularly bespoke methods, like change in deck switching between blocks, or what was described as an index for the stability of strategy or switching strategy, or the flexibility of it, and also in autocorrelations within participant in their switching behavior between decks. So again, we're presented with a relatively large number of scoring strategies given the number of articles we're considering. 28 general scoring strategies, not even unique ones, just general approaches to it, which can then be applied at an even finer grain level to subsets of trials in some cases, like do this for each of the first 20 trials and then the next 20 trials and the next. Producing a median of 6 scoring strategies per article, ranging between 1 and a eye-opening, let's say, 49. I've inserted one of my plots a little early here. I'll come back to this bit here. So the modal strategy was found to be the following: the C plus D minus A plus B. And this was used in 71% of the articles that we observed. This could be seen as positive in the sense that there is some degree of not standardization, but at least a common method of analysis. But the downside, or the less positive news, is that this is not the only strategy being used in many of these papers. So again, even when we see some degree of common normative usage, researchers often supplant that strategy with other more bespoke, novel, less frequently used ones. This raises the question of how much does this scoring method matter? Because imagine these scores produce scores that are so highly correlated that it doesn't matter too much. This is a quantitative question. In order to answer this, we have constructed a multiverse analysis where I take real IGT data from real participants. I calculate all known strategies that we find in our sample, and then I correlate all of those strategies. I calculate all of those strategies with the modal strategy in order to observe a distribution of correlations. As a quick aside, of course, a good criterion variable here might be more informative because, yeah, you could do work on at least speaking to which of these methods has the best validity of a certain sort. In the absence of that, until we can find a good data set to do this, these correlations with the modal strategy are at least a useful approximation. So what did we find? We find that correlations between the modal strategy and other strategies range almost between minus 1.0 and plus 1.0, with a nearly a relatively flat distribution in among it. So without being able to speak to what individual researchers did or may have done, it is certainly an option given the choice between these strategies that might be applied post hoc, that simply choosing a different strategy would provide wildly different variants to work with. So if the initial hypothesis tests don't work out, a huge opportunity for p-hacking arises. Naturally, there is then a risk that meta-analyses would synthesize these different scores, which correlate very poorly, even negatively, with one another as if they are equivalent. And this constitutes a strong risk of a jingle fallacy. The idea that because these are all treated as IGT scores, that they would be synthesized as equivalent, when empirically, the details of the scoring may matter so much as to make them, inappropriate to synthesize together. This is particularly problematic when we relate this back to the fact that many papers simply don't report their scoring strategies or their procedural details in sufficient detail to know. So it's not even the case that all papers could be, for example, more thoroughly meta-analyzed on the basis of what scoring strategy they applied, because in some cases, it's simply not reported in sufficient detail. Do we have time for one quick more, or should we move on to the wrap-up? What time are we at?
We have about 10 minutes remaining in the session.
Okay.
So it's up to you whether you'd like to continue or have some time for questions and discussion.
I can do this one quite quickly, so we'll just add some details. It's another in-progress study with Nathalie Miner. So again, in order to select tasks that are common in the literature, in order to see if we can paint a picture of what is broadly happening, rather than this being a unique problem for one or two tasks, we chose another common task, the NBAC task, said to be a measure of working memory and commonly used again in cognitive neurosciences. Very briefly, the procedure is that participants are presented with sequential stimuli. So one at a time, you would be presented with, for example, a series of letters where the order of presentation would be on screen, T, L, H, D, H, O. And on each trial, you would be asked to respond when stimuli are identical to N trials prior. So on a 3-back task, you can see that the C in red serves as 3 trials previous to the underlined C. So on the second underlined C trial, participants would have to provide a response that C was indeed presented 3 trials back. Okay. Again, we see very wide heterogeneity in procedural details when reviewing 100 papers using the NBAC, randomly sampled from a larger systematic search. Some studies present practice trials and some simply don't. Some provide an adaptive versus a static task where you have to reach criterion to move on to a more difficult stage. The number of total trials ranges really substantially between as small as 24 and as large as above 3,000. The number of NBACs, as in the number of trials on each task that you have to respond on the basis of, ranges from 0 to 8, including multiples. So you might have to do both 0, 1, 2, and 3 back, for example, but can be all sorts of combinations of those. And importantly, the base rate of trials that are indeed NBAC targets ranges substantially from as low as 14% up to 50%. And yet, when we read NBAC in a paper, it is of course tempting to treat these as mutually substitutable tasks, when clearly the procedural details vary so substantially that this is difficult or unwarranted to do. And then very briefly, the other details including of the procedural details, pardon me, include substantial differences in the responses provided, including whether the participant only has to respond to target trials, as in if it was an NBAC, if it was a 3-back, press the spacebar, or you have to provide one response to assert that it was 3 trials back and another to assert that it was not 3 trials back. There are also really substantial variations in the stimuli used, those involving pictures for some tasks and many different forms of pictures that involve different domains, letters and different combinations of letters, numbers and different variations in the combination of numbers, and even audio NBACs. So sometimes these are presented visually on screen, sometimes they're read out loud. There are also single and dual NBAC tasks where more than one modality might be presented to participants at the same time, and participants have to respond to whether it's presented on either mode, N trials back. Okay. Again, we see a really large degree of variation in the flexibility of how these tasks are scored. And these come again in multiple broad categories of how this can be done. So in adaptive tasks where participants only move on to a higher degree, a higher N in the NBAC, the highest N reached can represent the final score. If I manage to meet a practice criteria or a mastery criteria on 3-back, I'm given a score of 3. But the mastery criteria itself can vary. Equally, the scores were observed to the scoring methods were observed to involve metrics of speed, which could be both, for example, medians or more complex versions like penalized reaction times, but also variability in reaction time. So not just speed, but variability. And lastly, a large range of accuracy-based metrics, many of which related to signal detection and analyses metrics were also observed. So hits, as in it was indeed an NBAC and was correctly responded to. Misses, it was an NBAC and was not. False alarms, it was not an NBAC trial and was responded as if it was. And correct rejections, the final option. And unfortunately, within signal detection analysis, once you have hits, misses, false alarms, and correct rejections, you also have a large number of other metrics that can be calculated from it, most of which we find in the literature. So accuracy, which is hits and correct rejections, D prime, bias, A prime, and C. And as with the IGT and in Malta's analyses, once you have one of these metrics being used, you often find that it's being used on different subsets of trials. So differences in, for example, accuracy between in-participant conditions, like 2 different stimuli types, or other within subject condition manipulations. Again, the question arises of how much does this choice of scoring matter? So again, we take real NBAC data, scored via these methods. We see a more constrained range of possible scoring outcomes, as in the correlation between these various scores and the most common metric, accuracy, is lower this time, but still substantial enough that it represents a real threat of being a vector for p-hacking. Because if my most common metric doesn't work, I have another metric that scores only 0.25, for example, with that. That's easily accessible to me. So what do these meta-method analyses tell us? Clearly, across tasks, we have high variability in the task's settings, the procedural details, their computation. Without pre-registration of these details, these analytic strategies can be simply chosen post hoc, and there's good reason to think that they are in many cases. There is mass ambiguity about which is the right or correct or valid computational strategy, because especially with behavioral tasks, it's extremely rare for this to be presented alongside method of evidence of construct validity or superiority of one metric over another. It's really common that papers jump straight to hypothesis testing without showing much of any measurement or validity evidence. In the absence of this, it becomes increasingly difficult or potentially impossible to interpret these literatures, or certainly to synthesize them across studies. And this lack of standardization is a clear threat to objectivity. So how can they be used in future? Principled systematic examinations of methodologies such as these and others can be used to yield results that can at least inform the degree to which we can synthesize work like this. They can be used to inform subsequent meta-analyses because they tell you whether it is appropriate to synthesize at all in some cases. They can add to our existing toolkit of statistical bias estimation techniques, and they can uncover idiosyncratic deviations from the norm at either the article level or the field endemic level. And this is, as Malta said, in important contrast to what is often done in meta-analyses, where, as in through like TIVA and P-curves, where it's not possible to know based on results alone which of the set of implausible results should be scrutinized more closely. Scrutinizing methods through meta-methods analyses can provide you more fine-grained analyses of which papers are deviating from norms or whether norms exist at all. And it is, bottom line, a fairly conservative method because it is based on only what is reported in the publications. So unfortunately, even the metrics that we provide here are likely like lower bounds of what the actual degree of flexibility is. Okay, time for questions.